Everybody, welcome to Cq224D. Today we'll go over TensorFlow. It's a bit of an experiment in the sense that I don't think there's ever been a great deep learning class that already covers TensorFlow, so we're now really at the cutting edge of technology. As such, there's no really other good material you can learn from, and we're doing this experiment a little bit with you. So please feel free to ask questions during this lecture. I haven't been able to code as much as I'd like to in the last couple of months, so Bharath, who's been working with TensorFlow extensively the last couple of months, that it's been out only, is going to give today's lecture. In terms of organization, today the problem set 1 is due, so hopefully you're all on time. You have at most 3 late days for this problem set. If you have any urgent questions, do come to office hours. I can make some exceptions with my office hour today too, if you're stuck, although ideally mine will be about the projects. Thanks for all the ones who have come already to Project Advice office hour. I'll try to also keep track now and have a list, so if you come, let's put down your name to make sure we verify that you came to office hour for the project. We'll release problem set 2 tomorrow. It will be largely based on TensorFlow. Once you know TensorFlow very well, it's a very easy problem set. But that's a big if. So hopefully today is useful. I think we went over this last night, over this lecture, and if you pay attention, you could almost copy and paste things and it should always run. You should really be able to understand every line of code that we'll go over, that Bharath will go over. So do ask questions when they come up. Also, we've had around 40 people or so who filled out the class survey. Thanks to those 40. It looks like we improved the amount, so we're more like 55 to 60% of people think it's the right speed right now. If that was a sample bias, because all the people who are happy are more likely to take the survey, and you aren't happy, please do fill it out so we can adjust the speed accordingly. Because TensorFlow is non-trivial to set up and install, we'll have special sessions about TensorFlow this week, and then you can always, of course, ask in any office hour if you have any questions. We'll go especially over how to set it up in AWS, another very practical, useful skill these days. You can essentially start your whole own cluster if you want and run many more experiments in parallel. That's about it. Are there any questions about the organization, problem sets, office hours? No? All right, then take it away.
All right, so I think we could probably get started just by talking about what's the state of deep learning today. So for those of you who've been following kind of the deep learning public library, there's a kind of a zoo of libraries out there. There's like Theano, Keras, cuDNN, MXNet, et cetera, et cetera, et cetera. And if you've been following attention, each major company basically has its own deep learning library, and many academic labs have their own deep learning libraries. So before we even kind of dive into TensorFlow, you need to start asking the question, which deep learning library should we use, and why should we bother using it? What are the kind of axes of deep learning libraries, and what are the strengths and weaknesses that all the different deep learning libraries bring to the table? So I think there's a few axes you can use to kind of think about deep learning libraries. The first one I'd say is, when you are specifying a new deep learning model, are you writing a config file or are you writing a program? So some of you may have experience with, say, Caffe, or maybe some of you did an internship at Google a couple of years ago, and there was the disbelief system. And in these systems, when you want to make a new deep learning model, you're not writing code, you're writing basically a JSON file. So you write down a JSON file that specifies your complicated model, and once you specify this JSON file, it auto-creates the model for you. So in some sense, this is convenient because you can think of a deep learning model as kind of an object that you specify statically. And the nice part is that if somebody else specifies a deep learning model for you, you can copy paste the config file. You don't have to write new code. Now, the trade-off is, for anybody who's done a lot of things with JSON, you know that things get hairy quickly. For complicated models, for things like recurrent neural nets, for the very deep convolutional neural nets people use in practice, you get giant JSON type files floating around. So I think there's a story in the Caffe repo, which is one of the major deep learning packages. There's a 7,000 line configuration file for the ResNet deep network, which is one of the ImageNet challenge winners for this last year. And the reason is that network has something like 150 layers. So they basically copy the JSON config for one layer 150 times. So if you go into that, you see 150 repeats of a config file. So things get hairy with configs. So as people built experience with deep learning, it became clear that you don't want to have config file descriptions of deep learnings. You want to really have it be part of your program. You want to be able to use standard programming constructs like for loops or other programmatic constructs to construct the complicated deep networks people tend to use in practice. And I think in this problem set, you'll see a bit of that. We'll make you construct a recurrent neural net using TensorFlow, and you'll see how easy it is. It's basically 10 lines of code in a for loop when you do it programmatically. If you're going to do it with a config file, that would be a significantly more challenging exercise, and I think that was a research paper at some point doing it in Caffe. So let's assume now that we're going to stick with programmatic construction of deep learning models. The next question is, what language should we use? So if you've ever done a lot of numerical computing, you'll kind of know that numerical programs have to be written in kind of an optimized language. So for many years, this was Fortran. So you'd have kind of mountains of Fortran code sitting in the back end of all these national labs running things like nuclear simulations and the like. So today that's improved a little bit. You can actually use C++ to write high quality numerical code, and there's great libraries like Eigen that'll make this easy for you. But even so, writing C++ is not, in some ways it's like writing a config file. You have to worry about a lot of things that are not directly relevant to the learning task at hand. Things like memory management. So in practice, most people tend not to write C++ when they're making new deep learning models or even numerical models. Rather, you want to have a high-level kind of wrapper around the C++ that lets you call into the C++ efficiently, but lets you use the syntax and the memory management constructs of a high-level programming language. So there's really two contenders in the deep learning space. One is Lua, and the other is Python. So Lua is kind of a game engine wrapper. It's designed to have very quick interop from C to Lua, and the Torch library makes good use of Lua to write scripts in it and basically tie directly down into the lower level numerical code. So a lot of people really like Torch. Some people have some great stories with it, but the downside is Lua is not as mature an ecosystem as Python. So Python's really where a lot of the scientific community, the kind of programming community, the web community resides nowadays, and the convenience of having all these libraries at hand was something that we felt we couldn't give up on. So we decided, all right, so let's use a programmatic deep learning model, let's use one in Python, and what are the choices left? What languages, what deep learning packages will meet this criteria? So for those of you who know a little bit about deep learning trivia, you might have heard of the package Theano. So Theano is kind of a symbolic tensor manipulation package in Python. In many ways, it's kind of the forerunner of TensorFlow, and in some ways, it's even more advanced than TensorFlow. It's certainly a more stable package. It's been around longer. So you can ask, why aren't we using Theano? Why are we using TensorFlow? And part of it, I think it's that TensorFlow is new, it's shiny, that's one aspect. The other aspect is that TensorFlow has kind of more support for building giant models. So when you start building very large deep learning systems, one thing you might want to do is not just use, say, one GPU card to train your model, but you might want to use a whole bank of GPU cards. And if you start reading papers in this literature, you'll find things like, we trained on a bank of 16 GPUs for a week, and you can't do those types of experiments on a single GPU. So I think one place where TensorFlow really shines is the built-in support for distributed systems. So you can kind of build distributed deep learning models, and we felt that that was a skill that we wanted you to have, and that was better served by having you learn TensorFlow. But if you want to ever write models in Theano, you'll be able to use your knowledge of TensorFlow, and basically it's almost a one-to-one mapping, not quite, but you can port that knowledge over. So kind of for all these purposes, we decided, all right, let's go with TensorFlow, and actually, but we should say a couple caveats. TensorFlow is a very new library, so some of you might try Googling TensorFlow versus Theano versus X speed benchmarks. And one downside of TensorFlow currently is that it's actually a reasonable bit slower than most of the other deep learning packages on these benchmarks. So you lose something like 50% in speed on a single GPU today. But I know there's a lot of smart engineers at Google really trying to hammer away at that. So I think that part will be fixed. So assuming these things are fixed, these are kind of I just wanted to give you kind of a picture of the landscape before we dive deep into TensorFlow and start talking about it. So now that we've kind of gone over a bag of motivation, the question is, what is TensorFlow? Now, the obvious answer is, it's a deep learning library. It lets you build deep learning models. But if it's a deep learning model library, why didn't we call it DeepFlow or something? Why is it TensorFlow? And the answer is, at its heart, TensorFlow and Theano are not really deep learning libraries. They're basically numerical packages that make it easy to deal with these mathematical constructs known as tensors. And the idea is it's a package that lets you define arbitrary functions on tensors and lets you take their derivatives easily. Now, that of course begs the question, what is a tensor? And unless you have kind of extensive background in numerical physics, you might not be that familiar with the concept of a tensor. So I'll start by saying the things that a tensor can be. A tensor can be a scalar, a tensor can be a vector, and a tensor can be a matrix. And it turns out that when if you fix your math just right, and I have some details on the slide, and you can look this up, or you can go look in Wikipedia. A tensor is basically a multi-dimensional array of numbers. So for anybody of you who've played with things like Python, NumPy, you'll know that there's very easy ways to define, say, easy generalizations of matrices, kind of multi-dimensional arrays where you can say, if you have a three-dimensional tensor, you'd have three index variables, I, J, K. So you can kind of think about it as copies of a matrix that you can index into. So kind of the reason that tensors are so interesting and useful for machine learning is basically every operation you'll ever find in any machine learning paper can be written as functions on tensors. And in fact, this is a bit of a cute exercise. Any operation basically in the numerical chemistry, numerical physics, any numerical literature that you can find can be written as functions on tensors. So a neat little thing that they've done in the TensorFlow docs, you can go look this up, is they actually have a partial differential equation solver written in TensorFlow, which is really cute. It's the sort of thing that you wouldn't expect a machine learning library to be able to do, but it's kind of neat to know that it's there. That said, it's a terrible PDE solver. You don't want to actually use it for anything, but it's nice to know that you can. It's kind of reassuring. So another kind of analogy that I'd like to kind of come back to is that a lot of people don't compare deep learning libraries to kind of standard numerical libraries, but in some ways that's really the comparison we should be making. TensorFlow, I'd argue, is actually more similar to a package like NumPy, in that both of them are basically libraries built around these n-dimensional arrays. And the idea is that these multi-dimensional array manipulations are at the heart of both packages. So if you know NumPy, I'm going to argue that it's not that hard to actually figure out TensorFlow. Now, the things that TensorFlow gives you that NumPy doesn't, the biggest, I'd say, is that you can move things on a GPU. So there's a lot of code I've written in NumPy, and I've basically been copy-pasting it into TensorFlow with a few changes, and I'm automatically getting GPU usage and getting a 10x speed up in my code, which is a really nice perk. But of course, the other big one is that NumPy doesn't really talk about derivatives. So if you define a function on a NumPy array, you're responsible for finding the derivative of that function if you need to. And basically, like we had you do in the last homework, you can do some matrix calculus and figure out those derivatives. But as an aside, there are Python packages that'll automatically differentiate functions on random NumPy arrays for you. So in some ways, TensorFlow is, I'd say, a GPU version of NumPy with some extra intelligence baked in for functions. So let's kind of do a very, very quick recap of NumPy. Now, I hope all this is familiar to everybody here, otherwise you're going to have trouble with the homework that's due today. But the idea is NumPy gives us a bag of operations we can apply to various matrices. So in this case, we're doing something like we make a 2 by 2 zero matrix, one matrix and zero matrix. We sum it along an axis, or we might reshape it to have another shape. So these are kind of the standard array matrix manipulation operations that NumPy allows you to do. Now, the neat thing is that you can basically do exactly the same thing in TensorFlow. So there's a lot of kind of things going on in this slide. So let me just kind of talk through what's going on. So in the last slide, we said, let's import NumPy as NP. In this slide, we say import TensorFlow as TF. The next thing we will do is we'll say, there are a few bits of cabbage here that aren't directly mapped to the NumPy, and the little arrows on the screen will tell you what these bits of cabbage are. For now, you can ignore them, but kind of the heart is we can call tf.zeros to make a 2x2 matrix in TensorFlow. We can call reduce sum, which is the analog of the NumPy function sum, to sum it along an axis, and we can use getShape, which is the analog of shape in NumPy, and we can use reshape, which is the analog of reshape itself. So once you kind of have this back and forth between NumPy and TensorFlow in your head, it's not at all hard to start writing TensorFlow. You just do the same things you do for NumPy, and you kind of carry it over. And to help you along this process, we put together like a small dictionary. So a lot of the operations you can do in NumPy, you can basically carry over to TensorFlow. TensorFlow, one nice thing is it has syntactic sugar. So if you do things in NumPy, like you have a matrix and you multiply it by a scalar and you add another matrix, there are these complicated things called NumPy broadcast rules that make this all work out most of the time. And TensorFlow, luckily, has these same broadcast rules baked in. So you can actually do things like, say, 5 times a TensorFlow tensor will do what you think it should, just like it'll do what you think it should in NumPy. So kind of as a bit of a confession, when I'm writing TensorFlow code, I usually write a NumPy version, then I translate each function one at a time. And for the homework, this might be something you might want to do. Try writing something like the forward pass of whatever deep network we ask you to implement in NumPy, then just translate it to TensorFlow. If you know the function you're looking for, the TensorFlow API, you can, people on Stack Overflow have done half the work. You can say TensorFlow version of NumPy sum, and there is, in fact, a Stack Overflow post that'll tell you exactly what this is. So luckily, the large community that's built up has already made these things somewhat digested, so you can just use Stack Overflow in Google to figure out these tricks. So now, though, we're going to start talking about the ways in which TensorFlow is not NumPy. And the first one is that TensorFlow requires explicit evaluation. What does that mean? So when you call np.zeros and you make a 2x2 array in NumPy, you can display it directly. It is basically what you think it is. When you dive down into the C, it's a block of memory you've allocated that has zeros filled out onto it, and it's basically a call to malloc or something like that. But if you look at the TensorFlow code, that is not what's going on. When we call tf.zeros and we try to print it out, we get this weird looking tensor object. So in some ways, the heart of TensorFlow is that although it looks like we're doing direct operations on various multidimensional arrays, there's actually another hidden step. So we'll return to this concept kind of again and again over the course of the rest of this lecture, but the idea is that TensorFlow is a system for defining operations on these tensors, and it forms a structure known as a computation graph. And the idea is that you define a computation graph, and it's a symbolic entity. But the computation graph doesn't have any values till you run it in some context. So the key thing is that when we call .eval, which you might remember from all the slides previously, we're implicitly running the TensorFlow computation graph in a context. And if you remember that bit about tf.interactive session, that's a convenience that TensorFlow offers for you. So it's setting up a global environment. So TensorFlow computations, you can think of it as creating these functions on these multidimensional tensors. Then you're setting up an environment for those computations to exist. Then you execute those computations in that given environment. So when we actually do up here ta.eval, we're saying use the global environment, execute the computation specified by the tensor TA in the context of this global environment. And in this case, since TA is just a zeros, it does what we think it should. It makes a zeros array and it kind of prints it out to screen. So that's kind of the critical bit between TensorFlow and NumPy. NumPy is actually doing operations on memory the minute you tell it to do anything. TensorFlow instead, you're describing operations that you'd like to have happen. Then in some sense they're compiled and you execute those operations. So there's kind of this symbolic barrier in between. You can get around it when you're playing with things, but it's very useful to keep in mind that TensorFlow is not NumPy in this one way. So we were just talking about kind of the need for executing TensorFlow in a particular context. In the TensorFlow library, the object that encapsulates this notion of an environment is called a session. So the idea is that when you have a TensorFlow computation graph, and when you've defined some function on tensors you'd like to have executed, then you say, I'm going to start up a session. Then within the course of this session, I'm going to execute this computation. So in the previous slides, we used the function .eval, tensor.eval. That's actually just syntactic sugar underneath the hood. What .eval says is find the session that's currently in scope, execute the computation I asked in that session, and return me the result. So the key bit at the heart of TensorFlow is basically session.run. And this is a function we're going to see again and again, and session.run is basically how you interface with the TensorFlow computation graph. You have this abstract computation, you get this concrete environment, the session, and you run the abstract computation in the concrete environment to get a numerical result. And this is kind of the workflow that goes on in TensorFlow. And in this case, we have a simple example of doing something like that. We set up two constants, we multiply the constants, and the key thing is that C, that is A times B, is a symbolic value until we create a session and run the computation in that session. When we run that computation, we get out 30, which is what we'd expect. But 30 does not happen until we actually evaluate it. And here I'm just, yes?
So I'm assuming that if you had used two different interactive sessions, like TF1, TF2 for A and B, and then set that equal to C, everything would just explode.
Yeah, that's getting gnarly. So interactive session is just to make life friendly for you in the shell. It's not what you should be using. But if you set up two different sessions and you had A in the first session and B in the second session, ooh, that gets nasty. I'm actually not sure what would happen. It's the sort of thing that you shouldn't be doing. So you're welcome to try. Like TensorFlow is mostly polished, but every so often you'll do something and you'll see this explosion of C++ errors onto your screen. And that's a sign you're kind of taking the library in directions it doesn't support yet. But it's a fun exercise, I'd say. Try it out. There is, in fact, one thing I should mention. If you're going to start playing with this, I'll talk a lot today about computation graphs in TensorFlow. Now, TensorFlow, in all the code that we'll present in this class, we're going to have a global computation graph. It's going to be an entity that exists in the ether. But you can actually manipulate multiple computation graphs simultaneously in TensorFlow. So you could do things like you could set up A in one graph, B in another graph, and then they wouldn't be able to talk to each other. But again, this is a bit of an aside.
Is there a way to copy a tensor object without evaluating it into another session?
That is so the graph exists independent of the session. So computation graph is an entity that exists. So the various tensors exist in the graph. They don't require the session to exist. But the particular numerical values that they take on in one session need not have any connection with the numerical values they take on in the next session. So that's kind of the connection there. So here I'm just repeating some things I already said. Interactive session is a useful tool. And another thing, when you're debugging, use IPython, use interactive session, play with tensors and print them out. It's very hard to gain intuition for these things without actually running the computations, and interactive session is your friend. The other thing, again, here's a bit of looking forward. When we say session.run C, we're actually executing what in the TensorFlow docs is called a fetch. So fetch is basically, you have this abstract computation graph, and there's two operations, kind of jumping ahead. You feed, you put data into the computation graph, and you fetch, you take data out of the graph. So you can kind of think of the abstract computation graph as creating a program that you compile. Then maybe from the command line, you feed in some input args to the program you've compiled, and then you take some on standard out. So by analogy to these shell programs, the input args are the feeds, which we'll talk about in a couple slides, and the output args are the fetches, which we'll again come back to in a couple minutes. So again, just repeating things I basically already said. So computation graphs are the central entity in TensorFlow computations. Every time you call a function in TensorFlow, like when we go back, if you remember, I said tf.constant or A times B, you're actually, what that really translates to, you're saying is, find the global graph that is currently in scope, add these operations to that graph, and hold them within memory within that graph. So one kind of I'd say nasty thing about TensorFlow is that it functions with respect to a global graph that exists in the background. So it's not quite functional. In NumPy, when you say a times b, there is no global memory that remembers that you said a times b. In TensorFlow, there is this global graph structure that's recording every operation you make. So if you get weird things that go on, you might just want to sometimes close your session and restart it, or like Control-C it, because there's this implicit notion of memory that's handled through the global graph. And we've been talking about this abstractly. I put a couple of pictures in following this, so hopefully that'll help you gain intuition once we get to some more complicated examples. So we've talked about some operations. We've shown some basic examples of numerical manipulations you can do in TensorFlow. And until now, most of it's been basically copy-paste from NumPy. But in some sense, TensorFlow is more than just an array manipulation library. You could say it's basically a prototypical programming language, a very simple one. And any programming language worth its salt has variables. So variables in a standard programming language are basically boxes that hold state. So TensorFlow similarly has the notion of variables. And when you're building a machine learning model, all the parameters in that model you want to hold in TensorFlow variables. So you can think of, say, a weight vector in a machine learning computation as something that you want to put in a weight box. And you're going to go back and forth to that box and put things in and take it out and update it. So really the notion of having mutable variables is critical for machine learning. And so it's critical for TensorFlow, and we have this first-class object, the variable, to really help us get to it. So here we're going to kind of walk through a very simple use case of a variable. So a variable is a box, and like a variable in a standard programming language, a variable does not have a value until you initialize it. So in C or Python, if you use a variable without declaring it, you're going to get an error. Or in Python or JavaScript, I think you can actually get away, it'll be none or something like that. Basically, that's a good way to think about it. A TensorFlow variable is basically none. It doesn't exist until you initialize it. In this case, what we're doing is we're setting up, I think, zeros. We're saying, I'm going to make a variable w, let's call it weights, and this will stand in for, say, a weight vector of the type we might use in a machine learning language program. And we're going to initialize this weight vector with a zeros matrix. So one thing that you kind of have to keep in note is that TensorFlow requires you to be explicit about the notion of initialization. So in the former examples we've seen of TensorFlow, we make various constants and we just run them in a session, and they come out correctly. But you can't do that for variables. And the reason in TensorFlow logic is that variables don't have meaning until you initialize them. So until you explicitly initialize variables in TensorFlow, and you do that with the call to tf.initialize all variables, variables will blow up on you. And as you're getting used to this, you'll have a few horrible error messages that say something like uninitialized variables cannot meaningfully be used, or something like that. But the key thing to remember, the difference between a constant tensor and a variable tensor is a constant tensor doesn't have to be initialized, whereas a variable tensor, that is a box that holds value, always has to be initialized, and you always have to call initialize all variables, or its more advanced cousins, before you start doing computations on variables. But once you initialize them, you can do basically the same sorts of things. So you can use session.run and feed it in a variable, and it'll behave just like session.run fed in with a tensor, and we actually have a simple example of that on the screen. I said everything on this slide. There's kind of a dichotomy between constant tensors and variable tensors. Constant tensors, feed in, you're good to go. Variable tensors, you need to initialize them before you can start doing things with them. Once you initialize a variable, it behaves basically like a constant tensor, but you can do funkier things. You can play around with it. And here's a nice example of the sort of things you can do with variables. So if you remember back to, I don't know, Programming 101 or whatever intro to programming course you took, one of the first things you might implement in a programming language is something like the notion of a counter. That is, we have some variable, and let's say we set it to 0, and we're going to repeat an operation some number of times. And
does anybody have any questions so far?
Are we good? Questions? Yes.
Why do we need a name for the variable?
Good question. So again, it kind of comes back to this notion of a computation graph. So remember, when we do things in TensorFlow, we're implicitly storing the computations done in the global graph. So once we store something in the graph, there's a question of how do we get back to it? Like maybe I created this graph and another program elsewhere wants to talk to that graph. So you need some way of indexing into the graph, and the way you index is by the name of the various variables or nodes that are in the graph. So it's mostly convenient as a lookup key. There's things like get variable, which we'll talk about later, which allow you to query the graph and get out a variable from this graph. So it's just a convenient way of indexing into the global computation graph. Yes?
Why is the graph used?
Why is the graph used? That's a good question. I think the reason it comes down to a graph is actually technical. We've covered the backpropagation algorithm in lecture over the last couple of weeks. And basically it turns out that although we only made you do backpropagation to compute the derivatives of these matrix multiplies and the like, it turns out that backpropagation is actually general and can be extended to graphs. So if you have, I think, a directed acyclic graph, you can, thinking back to algorithms class, you can linearize that into a chain, and going forward in the chain, you can use the backpropagation algorithm to take derivatives backwards through that graph. So in some sense, kind of from a purist perspective, a graph is the most general data structure on which you can take the backpropagation algorithm. So if you're doing it, you might as well do it on a graph because it's general. The other thing is it's useful in practice. Recurrent neural nets are graphs. Kind of complicated convolutional networks are graphs. There are more complicated deep learning algorithms, things like attention models, which we might say a bit about, that are even more complicated graphs. So basically, you need the full generality of graphs because there are papers and useful deep networks where you have graph structures. And without that generality, you can't implement everything you want to. Yes?
So talking more about the graphs, so you mentioned before that TensorFlow is optimized for clusters and GPUs. So does TensorFlow in the backend handle all the optimizations to do that efficiently? Graph structure?
So that's actually a very good question. You need to handle it manually. It turns out it's very challenging to actually distribute computations across multiple compute units efficiently. So what TensorFlow does under the hood, and we won't need this for the class, is that you can actually say, put different parts of the graph on different compute substrates. So you can say, I want these parts of the graph on GPU 1, I want these parts on GPU 2, et cetera, et cetera, et cetera. So there are fine-grained ways you can kind of spread the graph out yourself over various GPUs, but there's no automagical way that'll do this. Like, one dream people often have is, well, can I just define a trillion by trillion matrix and have it spread out into the ether? But no, you can never do anything like that. All operations in the graphs must fit within single GPUs. But the nice thing is you can put different parts of the graph on different compute substrates, which is why this is a very useful, kind of answering your question as well about why graphs. It's a very useful technique for handling where computation is done, in addition to specifying complex computations.
So can I have a variable name, like two variables with the same name but different name tag, or maybe just different variable but with the same name tag?
So the question is, can you have different variables with the same name tag?
Yeah, because when you define variable, you have a name, right?
So it depends. Like, we'll come back to this again, but there's a notion of scope. So you can set up namespaces in TensorFlow to have, just as in Python, you can have, say, two variables with the same name in different functions that don't see each other. You can do something similar in TensorFlow. I think that a name does actually uniquely specify a TensorFlow variable once you expand out all the scoping, but in the same scope, two things that have the same name do refer to the same object. So it does uniquely specify, but you have scoping to allow you to reuse names, so you don't need to constantly keep inventing new names. Yes?
So just to follow up on the naming question, so state and counter both sort of refer to that variable. Right?
So the question is state and counter.
We say state equals variable, name equals counter. I was wondering, like, counter refers to it, but also state refers to it. We're doing test.run of state.
So I'm not seeing a counter variable. Which variable up there?
The first one.
Oh, sorry. I see. All right, this is actually getting to a bit of, so the question is really, the variable up there is named counter in the string, but it's called state as a Python variable. How do these two things talk to each other? And this is actually getting to a good point. Python namespaces and TensorFlow namespaces are different entities. So counter is an entity in the TensorFlow computational graph, whereas state is a local variable in our Python script. These two things don't know about each other. Counter doesn't know that in Python we're talking about it as state, but given state you can reference in and check counter by calling .name. State.name will give you back counter. So this is something that can trip you up. TensorFlow namespaces and TensorFlow naming don't talk to Python namespaces and Python naming, so you can think of it as pointers basically. There's something on memory in the global graph, and you have kind of pointers that you can call whatever, but that doesn't change what's in the graph unless you do it explicitly. Do we have any more questions? All right. Cool, so let's return to talking about this example. So the idea of this example, hopefully you've had a chance to look at it by now, is there's a counter and we're going to increment it. And the idea is we start by making a variable to hold the counter, and we call it counter. In Python we refer to it as the local variable state. And what we're doing is we have two operations. We have a tf.add operation and we have a tf.assign. So one thing to note is that when we make this new value that's calling the TensorFlow add operation on state and on the constant 1, we are not updating the original state. We're just making a new tensor in the graph that happens to have the value 1 plus whatever is in the variable counter. So it's only when we call assign to explicitly overwrite what's held within the counter variable that we update it. So you can look at the Python translations on the right to give you a rough sense for what's going on. Please don't take this too literally. Like this is at best a metaphor to help you think about what's going on. You shouldn't read too much into the equals plus 1 and all the things that are written in the comments over on the right. So most of the time you won't actually have to deal with assign, but if you wanted to do complicated things where you're updating variables or doing some type of complicated machine learning algorithm, this is the type of thing you'd want to do. In practice, various optimizers that TensorFlow has built in take care of doing these sorts of updates for you. So you usually don't have to play with variables yourself unless you want to. So we talked a bit about fetches, and the idea was that fetches are the way to get information out of the global computation graph. And we've typically been calling session.run on one tensor. Now you can just feed in a list of tensors and get the values for all those tensors out. So nothing new here, but the main reason I want to emphasize this is if you read the TensorFlow docs, you'll see the term fetch come up repeatedly. That's all fetch means. You're calling session.run and you're feeding in a list of tensors, and you're going to get that list of tensors back from the computation. The more interesting concept, actually, before we go there, I'll show you the first picture of what a computation graph might look like. So the first thing I want to emphasize is this is not what's actually going on in TensorFlow underneath the hood. This is just a picture to help you think about what's going on. But if you look at kind of that simple example we put up on the previous slide, we have 3 constant tensors that we've defined. And the idea is that the first constant, we set it to 3, the second to 2, and the third to 5. Then we take the second and third constants, we add them, we get an intermediate value, and then we multiply it by the first value to get out mol. And the notion of a fetch is in the giant black arrows that are at the bottom of the screen. Those are the things we're pulling out of the computation graph. This computation graph has nothing going in. Everything that's in there is already specified within the text of the program. But we'll see examples of where we feed in data and then we fetch it out. But this is a simple computation graph where we're just fetching data from the computation we're asking to execute. So, any questions here? Does this notion of computation and the graph begin to make sense? Yes?
So what if at one point in the computation we fetch intermed and then maybe like 50 lines later after some other steps we decide to fetch mol? Does it efficiently like keep track of what feature med was, or does it just start from scratch?
I'm pretty sure it starts from scratch. Unless you've updated the variable state. So if you've updated variable state, it has memory. If you don't, it's functional. So this is a purely functional computation graph, no memory. For people who've done functional programming, you'll like this. This is like, maps and reduces and all those good things. But unless you update variable state explicitly, there is no change in the memory of the system. All right. So now, of course, the next question is, we know how to fetch data from a graph. How do we put data into the graph? And there's a very simple trick you can do. You can call convert to tensor. So if you have any Python list, or if you have a Python NumPy array, you can just call convert to tensor within a TensorFlow computation. That'll directly pull it in for you. So when you're kind of messing around with TensorFlow in the command line, I suggest you do this. Just use NumPy to make some data so you know what it is. Pull it into TensorFlow and start playing with it. So this is kind of a good way to get started, a good way to start playing with things. But it is a little inconvenient if you want to do it in a program. So there is a more rich built-in notion of how to feed in data. And the key concept is what's called a placeholder variable. So a placeholder variable is a special type of variable, but in some ways it's a dummy variable in that you're not going to update a placeholder, or you're not going to do anything with it except use it as a receptacle for the user to put data in that'll be fed through the computation graph and computed upon. So placeholder variable is simply an input node in the computation graph. So the computation graph we saw a couple slides back, that didn't have any input nodes because we didn't have any input in there. But we'll shortly in a few slides come and see an example of computations where you do have placeholder nodes to feed in data into the network. So here's a very simple idea of how you might use a placeholder. So we're going to define two placeholders. We're going to specify their types, their floats. So the way you should think about it is input 1 and input 2 are two variables whose type you've declared is a float, and there's nothing more known about them. So when we call output to be to be input 1 times input 2, output is a purely symbolic variable because there is no numerical value associated with it. And this is where it's useful to think about the computation graph. In the computation graph, it's a simple node, perfectly well defined. But if you try to do this in NumPy, for example, it's not clear how you do that translation anymore because there's not a notion of dummy placeholder values in NumPy. So the idea is that we make a concrete instantiation in the session, and we call session.run again, but there's one new bit in this, and that's the feed dict, which is kind of over in the corner there. So the idea of a feed dictionary is that it's a mapping from placeholder variables to concrete numeric values. In this case, I think we're setting 3 and 7 and 2 to the two inputs. So we're saying input 1, I want that to be a 7. Input 2, I want it to be a 2. So you can kind of think about it as a command line program where you have dash dash input 1, 7 dash dash input 2, 2. So each time you run the program, you can use a different feed dictionary, and that's analogous to kind of calling the program with different inputs. So when you execute the computation by calling it run and use the fetch on output, you get back the value of output. So you use the feed dict to feed in value to the computation graph, use the session to execute that computation, and fetch the value of output, and you get out 14. Now this seems like an awful lot of trouble, but this is a very convenient metaphor to have, and we'll find it useful as we kind of go further into the discussion. So, yes, go on.
At what stage, so for example, if you declared them to have different shapes that were incompatible, at what stage would TensorFlow give you an error? Is it when you try to run it, or when you try and just do the multiplication?
Oh, that's a good question. I think it is when, the question is that if you have incompatible states and you multiply them, when does TensorFlow give you an error? When it's defined or when it's run? I think it's when it's run. I don't think it has compile kind of declarative guarantees when you actually do it. I might be wrong about that though, but I think it's actually when you run it, it'll start blowing up on you. And TensorFlow is finicky. It does care about these things. NumPy is kind of nicer. It'll massage things for you if it makes sense. TensorFlow, you actually have to care about these things. So I am actually we're actually running low on time a bit, so I want to get to a big example. So I'm going to hold off on taking questions for a bit and try to get through to the simple linear regression example that I think will help you with the homework. So let's save questions for the end for the next 20 minutes. So here's kind of the one improved version of the computation graph we saw previously. Before we had kind of a fetch. We took data out of the graph, but there was nothing coming in. In this case, we have a feed. So that's kind of the dictionary that's put up on top that specifies the data flowing in. So the way to kind of read this graph is that the part in the middle is a computation. You have this multiplication op. You have a feed coming in up top that pushes data into the graph. And you have a fetch that pulls it out in bottom. So very, very simple. Again, for this, it's not even worth the trouble almost of drawing it. But when you start getting to more complicated operations, it helps to have this abstraction and this way of kind of thinking about these computations when you're playing with this. So before we kind of go into a more complicated example, there's one concept which you kind of touched upon in a question earlier, and that's namespacing. If you have variables floating around in any programming language, you need some notion of scope. Otherwise, you're going to have like temp1, temp7, temp39 floating around. So if you don't have some way of controlling the scopes of various variables, you're not going to be able to build complicated programs. And in TensorFlow, the key things we use for that are variable scopes. So variable scope is basically a simple way of introducing a scoped environment into TensorFlow. And getVariable is a way of retrieving a particular variable that respects scope. So this sounds terribly abstract, so we'll walk through a couple examples to kind of see what's going on. So underneath the hood, the namespacing in TensorFlow is much like the namespacing in the file system. It's very simple. So we have here two nested scopes, foo and we have bar. And when we nest this, what you see is we're basically just adding foo slash as a prefix to the name of the variable. And here we've called it v, and it's in the foo bar environment. So we have foo slash bar slash v, and we have :0 to name that to indicate that it's the first variable named v, in that environment. So for our purposes, we're not going to worry too much about the :0. The part I think it's important for you to get is the foo slash bar slash. So you have scoped environments and you have scoped names that let you hold models. Now this won't be terribly important for simple examples, but when you start building complicated structures, complicated recurrent or convolutional networks, it does become important to start thinking about namespaces, because otherwise you can't build the complicated deep learning models. So this is just a simple programming language primitive that you should all be very familiar with, and it's the TensorFlow analog of that primitive. There is one other thing that namespaces do. So one thing in deep learning models that you often want to do is the notion of what's called weight sharing. So the idea is that you have some idea, some belief about how a model works. And you might say that in something like a recurrent neural net, there is some operation, some transformation that exists at each step in time. And that's how we get from the present to the future. And this transformation is the same at every time step. And this maybe agrees with our notion of reality. If there's some type of description of reality, there's the same underlying process happening at each step. Now, the way you represent that in a machine learning model is you do something like weight tying. You say in a recurrent neural net, the weights that we use at one time step t are the same as the weights we use at t+1. And TensorFlow has a very convenient way of dealing with this type of weight reuse, and the idea there is to use the variable scope to control this. So there's a reuse variable in these variable scopes, and when you set, by default, reuse is set to false. So when you ask for get variable, you're making new variables each time. It's creating a new variable under the hood for you whenever you set reuse to false. But when you set reuse to true, you can find variables you've already created. And in something like a recurrent neural net where you're going to reuse the same weights at each time step, this is exactly what you want to have under the hood. So here's a simple case where we have this scope foo. Then we call getVariable, we make a new variable there. Now we say reuse variables, and then we call getVariable again, and we get back the exact same variable we've called. If you try this without that getScope, it'll actually blow up on you. It'll say, wait, there's two variables named v, I don't know what to do anymore. bam, and it'll crash. But if you set this, then you are basically using weight sharing. And this is very convenient for building complex models, and you'll need it on part of the homework. So we do have, I think, some time. Are there any questions about variable scopes and how they're used? All right, cool. So I think we've already talked a bit about what getVariable does. The key idea is that depending on what's going on in the global scope, it does two different things. The first is that notice that getVariable respects scope implicitly. If you call getVariable in scope foo, it'll look for foo/v. It won't look for bar/v or any other scope. So getVariable respects scope underneath the hood, which makes it sort of a convenience. If reuse is set to false, getVariable creates new variables for you under the hood. So it's kind of the preferred way of making new variables deep inside a TensorFlow program. But on the other hand, if you set reuse to true, then what getVariable is going to do is it's going to search for a variable that exists in the computation graph that you've just created previously, and when it doesn't find it, it'll blow up on it, it'll throw a value error. If it does find it, all is good. We just find the same variable again. And here we basically repeat an example much like the one we showed. And we can kind of come into and come out of variable scopes at different parts of the computation. So it's a very nice way of, you could say, encapsulating regions in the computation graph and saying this part of the computation graph is a conceptual whole, and I can enter and exit that part of the computation graph. So I still think this is all pretty abstract, so let's jump into, I think, a simple example, and I think this will help tie all the concepts we've talked about today together. So in many ways, the simplest prototypical machine learning algorithm is just linear regression. So you have some input variable x, and there's some output variable y, and we want to learn a mapping from x to y. And in this case, we've instantiated a little bit of sinusoidal-ish data. So we have a linear-ish increase in y as x increases, but there's some type of sinusoidal noise that's in the data. So nothing fancy, very simple one-dimensional learning model. So how do we actually use TensorFlow to build a model on this data, and how are we going to put in all the pieces of TensorFlow mechanics we've learned to actually construct something? So this slide has mostly cabbage, but there's a couple of concepts we've seen here that I'll come back to. First, we need placeholders. If we're going to define a computation in TensorFlow, we need some way of putting data into the machine. And in a machine learning algorithm, we have input training data that we want to feed into the computation graph. So you're going to start by making x and y placeholder variables that'll take in the training data and the labeled examples and use them to train the machine that we've defined. And you see a little bit in there about TensorFlow being finicky. So we do have to do some reshapes to make sure the shapes match out nicely. And I think the best way to do this is just write down what you think is reasonable. It'll blow up on you, and just make whatever small fixes it tells you to. So not that bad in practice, but it is something that hopefully they'll clean up moving forward. So now we kind of come to the actual heart of the linear regression algorithm. So we have kind of the model mathematically is we have some rule, some weights w, we have some bias b, and the rule we're learning is a linear function y equals wx plus b. And the idea is that conceptually w and b all fit within kind of the same scope. They're a linear regression module. And when we're having a deep network, you might have, say, the fully connected part variable scope. You might have the convolutional variable scope, the recurrent variable scope. In this case, it's a very simple variable scope that is just a linear regression variable scope. And we make two variables. We make weights and we make a bias. And since this is a very easy one-dimensional example, we say, okay, the shape is just 1 by 1 for w, and again, just 1 for the bias. So these are both one-dimensional variables that we put in. Now, we have the two variables. We have the placeholders x and y for the input data, which we defined in the previous slide. We have the two weights, w and b. Now, what is it that we're actually computing with? And in machine learning, the central thing is, the loss function, j. So what is the function that ties the variables in the model to the data? And here we define the loss. And the loss is simply going to be the L2 loss. We're going to say, y minus wx plus b. Let's take the sum of squares over all the x and all the y, and that's going to be our loss function. Now, how do we define that in TensorFlow? Okay, we have y, a vector of labels, we have x, a vector of inputs, and we have w and b, these constants. So just do the tensor arithmetic, y minus wx plus b, and square it. And now you have a tensor of size number of samples, which is the component-wise error, and then you do a sum to get out the total loss function. And you can kind of piece together how this relates to the symbolic mathematics. The reduced sum is kind of like the sigma in the kind of the written out math, and the y minus wx plus b is basically the y minus y pred squared part. So are there any questions here? Yes?
Do you need to use the TensorFlow add function to add b?
Do we need to use the TensorFlow add function to add b? No, because this is one of the nice things. TensorFlow does some limited broadcasting operations, so it'll figure out that, okay, wx is a tensor, b is a tensor, do component-wise addition of the tensor. So you don't need to use the dot add. Syntactic sugar takes care of it. Yes?
So here using tf.getVariable, could we also just do tf.variable?
Ah, I see. I think you can. It's when you're using a variable scope, it's good practice to use getVariable because you might want to use weights again in another part of the graph. And if you use getVariable, it'll respect the scopes and it'll handle the underlying namespacing. If you wanted to do it yourself, you probably want to say something like linear regression colon weights or something, and which gets nasty. So this is just a nice way to do it that you should do in practice. Oh, and I don't know if I repeated the question. The question is, do we need to use getVariable, or do we need to, or can we use dot variable directly? And the answer is you can use it directly. It's just messier. Yes.
The reusing there is the same of copy numpy.
Sorry?
The reuse variable parameter in this get variable is the same of copy numpy.
I'm sorry, I don't understand the question. The reuse variable is the same as copy numpy?
Copy matrix in numpy.
Oh, I see, I see. Is it the same as the copy matrix in numpy? No. So when we call numpy.copy, we're actually doing a memory copy. There's a region of memory that is in some matrix, and we're going to copy it to another region of memory. When we do reuse variable, we're saying, are we going to use the same node in the abstract computation graph, or are we going to use a new node in the abstract computation graph? So the key thing is, remember, nothing happens in memory, no computation is executed until you create a concrete session. So this is all an abstract construction, and this is just a graph that that we've defined symbolically. Any questions? Yes?
So x and y have to be placeholder variables?
X and Y have to be, yes, basically because you want to feed in user data to fit a model. You could make them whatever variables you wanted to, but if you want to fit a learning model, you do need placeholder variables. You do need X and Y to be placeholder variables. Cool. All right. So in the previous slide, we defined this variable loss, and the loss corresponds to the function j that we use in machine learning practice. Now, of course, as you're all familiar with, the key thing we want to do is del j, del w, or del j, del b. That is, we want to be able to find the gradient of the loss with respect to the parameters that define the model in order to be able to learn. Now, how do we do this in TensorFlow? So the nice thing is that TensorFlow implements a limited form of automatic differentiation. So for most cases, we don't actually need to minimize losses ourselves. We can instead use TensorFlow's built-in suite of minimizer objects or optimizer objects. So the idea is that an optimizer is just another node in the abstract computational graph. And it's a special node, and it's one that if you pass in some scalar tensor, in this case loss, it'll figure out what it has to do to optimize that under the hood. So if you remember back to the assign variable, the assign operation in the counter example, underneath the hood, the optimizer is doing something like an assign operation. It computes the gradient of loss with respect to the various variables in the network. Then it uses assign to do an update to those variables. And in this case, we're using, I think, the Atom optimizer, which is one of the family of optimizers. But for a simple example, you can think of this as just a gradient descent step. There's some theta old, you have some del theta, some update term, which you've computed, and you're saying theta new equals theta old plus some fraction lambda times the update, del theta. So it's the basic gradient descent step that we've had you implement many times. So underneath the hood, you can think of an optimizer as performing this update for us, and it helps save us some thinking. Questions?
What is Atom optimizer?
Oh, so Atom is just a convenient optimizer. You don't need to worry. That's in some ways, the question is, what is the Atom optimizer? And it is a particular type of optimizer. There are many advanced variants of gradient descent that are more or less stable for different models. I think the reason I chose to use Atom here is I think you'll use it in the homework. And the nice part about TensorFlow is that it encapsulates a number of these optimizers for you. So you don't necessarily even need to know what Atom is in order to use it, as long as you can make that API call. That said, it's a well-written paper, so I recommend Googling it and checking it out, or asking one of us at office hours about it. But it is a type of gradient descent algorithm, which is useful in practice. All right, yes?
In terms of its partial support for automatic differentiation, how, do you know if it will automatically differentiate the whole sigmoid function in one go, or will it decompose it into, the sum and the division? How optimized is that automatic differentiation?
That's actually, the question is, how optimized is automatic differentiation? And if you have something like the sigmoid, is it going to decompose it internally, or is it going to do a more optimized thing to handle it? And the answer is it really depends. So I think for something like sigmoid, I think you can implement it yourself. You can use TensorFlow.exp and various things. And in fact, no, we don't ask you to do that in this. We ask you to implement softmax in this homework with TensorFlow, and we ask you to do it using TensorFlow primitives. But for simple things is fine. If you have a very complex operation, it might become slow doing it the fully general way. So I think underneath the hood, you can actually replace some of these operations and have kind of shortcuts. But for this, you need to write new TensorFlow code in the C++ API under the hood. So you can do it, but it's more like if you're a developer working on TensorFlow. If you're a user, you should try to kind of stick with the primitives because it's just much easier. It might be slower, but it's probably good for a first prototype. That, or you can buy a bank of GPUs and just use that, and it's all okay. All right. Any more questions? So we should move on, because this is actually still pretty simple. This is just one gradient descent step that we're showing here. How do you actually learn a model? And this is where it starts to get a little gnarly. There's a lot of things going on in this slide, so I'll just say a little bit about the general idea without diving into details. When you're doing learning with gradient descent, the idea is that there's some number of steps you're doing. And in each step, you're taking a fraction of the input data. And upon that fraction of the input data, you're computing the derivative of the loss function on that input data with respect to the parameters that came in. And based on those derivatives, you're going to do an update to the variables that you've stored. And this TensorFlow code basically does exactly this for you. It's saying that there's some number of steps, 500, which we're going to take. At each step, we're going to take our input NumPy arrays. And by the way, this is one of the really nice things about programmatic design deep learning APIs, is you can do things like, I'm just going to randomly sample my NumPy matrix using random choice. Whereas if you're going to do it in a proto language, you have to do horrible things like write down random files on disk where you've pre-shuffled and then written down a shuffled version on disk. Whereas here, it's just so much nicer. You use NumPy to do random subsamples for you, and you can do things on the fly. So we take a random subsample. I think our batch size here is whatever our batch size is. And then we say, all right, let's just use the optimizer that we defined in the previous step to take one gradient descent step on this mini batch. So this is kind of composing all the various operations. So this is kind of abstract. So it might be nicer to kind of look at it visually. What is actually going on? So this is a complicated diagram, so let's kind of break it into parts. So if you remember sort of the visual language that we've set up, fetches are the black fat arrows. They're the things that come out of graph. The orange things coming in up top are the feeds. It's where you put data into the graph. So the idea of this graph is that we're computing this cost function, which we put up on the screen. And we feed in some data, that is the mini batch of data that we're putting in. We pulse it through the graph, and we fetch out the optimizer. And the idea is that one fetch of data from the graph, given a feed of the mini batch, is going to execute a single step of gradient descent. So the for loop that we saw in the previous slide is basically, you could say, I kind of like to think about it as a wave almost, like you're putting in data, it's like pulsing forward through the graph, and you fetch it out. And you're repeating this like data motion 500 times in the computation. And that's what TensorFlow is. It's a system for defining computational graphs to compute functions, and in this case the function we are computing, which might be easier to read from the math, is just this L2 loss thing. We define this function as a graph, we put in data, and we pulse it through the graph, and we pull out the loss, and we use a special optimizer to update the internal state. And we do this 500 times in a for loop. And this is kind of the heart of what is going on in TensorFlow. So I think here I'm going to pause and take questions, because this is the critical bit of what's going on in TensorFlow. So, floor open.
Can you go back to the slide?
Yes.
So why is there a underscore? You don't care about it?
So the question is, why is there an underscore? And that's just a Pythonic style. If there's a variable that for some reason you need to have returned to you, but you don't really care what the value is, you use an underscore. In this case, that's the optimizer operation. So we want to fetch the optimizer operation from the graph, but in some sense we don't care what it returns. We just wanted to do the update to the internal state. So this is actually a way of just documenting in our program. We don't really care what's the output of the optimizer operation. We just wanted to update internal state within. Yes?
So what would be an operation? Could it just be some machine auto returning something?
So an operation in this case, the optimizers, for example, there's a gradient descent optimizer or an atom optimizer. Those are operations. So we didn't really go into what a TensorFlow operation is, but they're just, you can think of it as parts of the computation graph that do things like update internal state, but they're just parts of the computation graph like everything else. And I think, in fact, addition or multiplication is an operation. They don't even have to update. It's just some transformation of tensors that's computed internally within the graph. And the question was, what is an operation, and do we have to know much about it? No, not really. It's just a part of the graph. Yes?
Is there an easy way to tell TensorFlow to run that for loop in parallel and just update asynchronously?
That's a good question. So the question is there a way to make this for loop run in parallel and just have TensorFlow take care of that underneath the hood for us? I think the way you do this is basically, that's a good question. There is a way to do this. There is a way to set it up and do a distributed gradient descent workers. And I think I'm a little fuzzy on this, but I think you define a function and there's some type of broadcast. You say that you're going to do it on a variety of GPUs. I don't know, I haven't looked into this carefully, and it just came out in the supported API. So I'm going to punt on this, but yes.
You're doing random choice, right? Wouldn't it be better to just have your data sequentially loaded effectively? So, i.e. going over the batch if it's large enough to just take the chunks?
So the question is, why do random choice in gradient descent? Usually random choice is actually helpful for maintaining stability of a learning model. And when this becomes really useful is if you have if different parts of the data are qualitatively different from other parts of the data, and you have a large enough data set, models exhibit what's known as forgetting. So like if you start, say, with the data from 2 years ago, and you work your way up to sequentially to the data from yesterday, the distribution of data from 2 years ago ago might be really different from distribution today. So there's a lot of forgetting that could happen. You could forget the patterns that came in the past because you're learning the patterns in the present. But if you do kind of this jumbled shuffle, you have to account for all the data. You have to account for a random sample of the data, which means the model can't forget. So in practice, it's healthier to do a random subchoice when doing an update to the model, because that ensures you've got everything in there. Questions? Are we good? Yes.
So I think, I don't know, maybe he wasn't asking that, but what is it advantage of doing a random choice versus a random shuffle and then sequentially going through the data like that?
So the question is a random choice versus a random shuffle?
Yeah. So
I see. Okay. So why not just randomly shuffle the data once and not worry about it? Yes, absolutely, you can do that. There's no difference in practice. This is just convenient, and I was hacking together Python scripts, so I was like, why not? If you have a large enough data set, you might not want to do this choice in real time, because that'll get you cache problems. You're right. So it is, for large data sets, it's probably smarter to do a shuffle before time and write it down.
But you do want every batch to have a different shuffle, every epoch.
Yes.
Is there any kind of practical suggestion for the batch stats, like optimal performance in the regression or neural network?
So the question is there a practical suggestion for what a batch size should be? And the answer I found is something like small powers of 2, 32, 64, 128. There is really, it's in some sense it's a hyperparameter. It's some aspect of the model training that really depends on your hardware, on your particular data set. You just, I'd say try out a few on your validation set, see what works better. Most of the time it doesn't make a big difference. Like, yeah, batch size 1, probably don't want that. Batch size 50,000, yeah, probably don't want that. But anything in kind of the smaller regime, it's mostly all the same. You can try out a few things. It's basically a hyperparameter. Try it out empirically. There's no real good rule of thumb. All right. We do have a few more slides, so I'm going to break here if there are no more questions. Okay. So here again we have this complicated graph thing, and it fits a nice model. So you can see it learned the straight line. So machine learning works, TensorFlow is great, we're done, we're out of a job, you know. You can write tiny scripts. So basically, this is kind of a toy learning example in TensorFlow, but all the programs that you'll write for doing non-trivial learning in TensorFlow will have very much the same structure. You'll have these for loops, you'll define this computation graph, that is your model up front, you'll take in your data in placeholders, you'll have a for loop in which you take some fraction of that data, then you'll run the graph one time, that is the model, that'll update the parameters in that model, and you'll repeat until you feel you're done. And what done is depends. There's many. In practice, you should be doing something like tracking error on a validation set, because this was a tiny toy example. We didn't do that, but in practice, you should not be doing what I'm doing on the screen. You should be doing something healthier, and the homework does make you actually look at error on a validation set. But for now, this is okay. So the one thing we really didn't talk too much about today is that how does this automatic differentiation happen under the hood? And I think we touched upon it a little bit in a question, in that it's just a backpropagation algorithm that you've already learned a bit about. And the idea is that when people were defining TensorFlow, as they defined things like addition, multiplication, or exponentiation, for each operation, each primitive, they wrote down a gradient function associated with it. So each TensorFlow primitive underneath the hood has had somebody write down a paired gradient function. So if you have exponential, you have a gradient of exponential function. If you have addition, you have a gradient of addition function. And the idea is that when you build up a graph with these primitive nodes, when you're doing the forward pass, you use the function, addition, multiplication, exponentiation. When you're doing the backward pass, as in backpropagation, you use the paired gradient function. And you use that just to use the calculus chain rule and propagate information through the graph. So there's nothing that magical. In fact, it's not that hard homework exercise to just do this and write like a mini automatic differentiation. And I'm actually the one writing this homework, so I was thinking of actually having something like that in there, but I decided not to. But it's not that bad. It's something you could do, and it's something that you shouldn't think about TensorFlow as magic. It's just doing some simple math underneath the hood, but it's nicely implemented so you don't have to worry about it. So practical suggestions. I think we've touched on many of these already. I think the key thing is that when you're getting used to TensorFlow, it helps to think about it as sort of a NumPy wrapper. Try doing things like writing functions in NumPy, convert the NumPy arrays to tensors, print things out. Things that will trip you up. TensorFlow is fastidious about things like shapes and types. So you'll get things like int32 given where float 32 is expected. Simple things like that, it's not serious, just figure out what TensorFlow is asking for, what it's expecting, and it'll work out. One thing that will trip you up is that some operations that are very natural in NumPy are not directly supported in TensorFlow. So NumPy, you can do nice things like index into a multidimensional array with another multidimensional array. And if you're going to implement softmax in the vectorized version in NumPy, there's a very natural way to do this. And some of you might have even used it in the last homework. That natural implementation won't actually work out in TensorFlow. There's like open GitHub issues and people complaining, so I think they'll fix it, but you'll have to be smart. So a lot of beginning with TensorFlow is about knowing how to start from the NumPy version and then distort it to work within the TensorFlow API. And we'll give you some exercises that'll make you work through this process and kind of internalize it. The other thing, again, is interactive session is your friend. Use IPython, debug things. The TensorFlow API is a little dense at times, so it helps to know what you're looking for. So try writing a version in NumPy, do a translation one at a time, use tools other people have already built to help you. Just look at it in Stack Overflow or something. So kind of doing a translation is easier than trying to write it from scratch. Another thing which we didn't touch on in this lecture at all is TensorBoard. So one of the really nice things about TensorFlow is it gives you kind of a visualization toolkit to look at models you've created and to look at the learning process as it's happening. Now, we're not going to use that much in the class. The main reason is that TensorBoard is kind of built to run on your local host. If you want to use it running on a remote server, you need to do things like SSH port forwarding, which gets a little hairy and we didn't really want to make you deal with it. It's a nice tool. If you're going to do your projects, you might look at it if you're having trouble, but you don't need to do it for anything that you'll use in this class. But we encourage you to play with it on your own time. So, kind of the most important question in the last minute is, where can you use TensorFlow at Stanford? And the answer, I think, for most of you is just go on Corn. It's up on Corn now, so you should be able to log into Corn, load up the TensorFlow module, and run the computation. And for the homework, we don't need you to use a GPU. You should be able to run all the homework on the CPU Corn implementation. If you do have access to a Stanford GPU cluster, something like Sherlock or Xstream, feel free to use it. Like, it'll make life faster, but the homework is made to be runnable on a CPU implementation, and you should be fine. If you want to do things like experiment with AWS and GPUs, we'll have a special session. Xiaojing, one of the TAs, is going to host a session telling you how to get up on AWS, and we have a machine image that will make it easy for you to start running TensorFlow. So go to his session on Sunday. And as a final thing, here's just a little hint for the homework. So in the homework, you'll have to define embedding matrices, and these are here are just some functions that you might find useful. So just take a look at the slides if you're stuck on the homework. And with that, I think we're done. Are there any last questions? Yes.
Yeah, if you go back to the for loop that had the optimizer code, how do we ask the optimizer not to optimize certain variables? Like, for example, if I added regularization to my loss function and I didn't want it to optimize the lambda scalar multiple of the regularization, how would I ask it not to do that?
Oh, that's a good question. Easiest way, just remove it from the graph. I think there is a way to set a variable to be non-learned. I'm not sure about the API version, but I think you can do this. In practice, a simple way is just to comment out that part of the code. But the question is, how do you ask certain parts of the computation graph not to be optimized? And I am reasonably certain there's a way to do this, but I don't know off the top of my head. question.
So in terms of the computation, let's say I have L1 loss or ReLUs or R10H. Does TensorFlow handle the pointy bits when you do the differentiation?
Good question. So if you have a non-differentiable loss function like a ReLU, does TensorFlow handle it? And yes, it does. Underneath the hood, it handles it by ignoring it. It turns out that you almost never hit the pointy bits, so you can just pretend it's all hunky-dory, and it works out basically all the time. And on the pointy bits, you just pick one of the sides to kind of pick your derivative. And the convergence proofs, like, for those of you who are interested, Steve Boyd's class talks about this in convex optimization. There's like subgradient convergence theorem, so things all work out on the pointy bits. In practice, you just pretend it's not there and it's fine. All right, cool. Well, thank you for listening, everybody.